Hello, my name is Stuart Franks, a Technical Product Manager for Alces Flight. I want to welcome you to our State of Practice talk at AWS HPC, Rapid Repurposing, how the foresight to replicate the HPC cluster in the cloud fueled the University of Liverpool's COVID-19 research. This project was able to take place thanks to the partnerships between the University of Liverpool, Alces Flight, and Amazon Web Services. I'd also like to thank AWS for their generous grant from their COVID-19 Global Disaster Fund for researchers, and mention myself and Alces Flight for donating additional compute management time towards the project. Here's a brief look at the agenda of our talk today. We're pleased to have representatives from each of our partners available to give insight into how this project was a success.
My name is Cliff Addison, and I am the manager at the Advanced Research Computing team at the University of Liverpool. Liverpool took delivery of our new cluster from Dell, working in collaboration with Alces Flight Limited and AWS in late 2017. Alces Flight handle our cluster software stack and provide system support and maintenance. AWS provided the university with research credits to explore how to augment our on-premise system with cloud resources, and Alces Flight actively assisted the university with these investigations. The on-premise system makes extensive use of Dell's quad-node C6400 chassis to house nodes based around 20-core Skylake and Cascade Lake processors. OmniPath provides a 100 gigabit per second interconnect. The cluster GPU nodes are a significant part of the university's GPU inventory and are in heavy demand. Additional GPU nodes are always part of any systems upgrade, and providing some level of access to GPU resources is an important part of any cluster resiliency or disaster recovery planning. In 2019, our Barkla cluster was to be rehoused in 6 water-cooled racks in our data center a floor below its initial location. This would require an outage of around 2 weeks, so provision was made for some alternative computing infrastructure, but we wanted the environment for this temporary infrastructure to be as similar as possible for our users. Hence, Cloud Barkla was born. Cloud Barkla replicates user authentication and authorization, along with their home file store. In addition, the application stack is as similar as licensing allows on the cloud and on-premise systems. The cloud infrastructure can vary with user demand and requirements. In 2019, both the Cascade Lake nodes and the GPU node were used heavily on Cloud Barkla. Cloud Barkla therefore provided us with a resilient framework for service disruptions, but its ease of deployment also meant that it was an ideal basis for cloud bursting, and that became very relevant in 2020 with the outbreak of COVID-19.
Hi, my name is Kristen Merritt, Project Manager for Alces Flight, and I will be taking you through an in-depth view of the Cloud Barkla setup and configuration. Thanks to the legwork done by the University of Liverpool's ARC team on creating Cloud Barkla in October of 2019, we had already gathered knowledge in how to test, scale, and run workloads in the cloud, which complemented the on-premises system. This transformation work, which allowed their physical cluster to be moved with little disruption to their users, would serve the Alces team well for the work that was to come in early 2020. With the outbreak of COVID-19, the University of Liverpool immediately put their HPC services to use on diagnosis and treatment. Dr. Yelin Zhang and his team at the Department of Eye and Vision Science were identified as candidates whose research would function well within the Cloud Barkla environment. For the team at Alces Flight, moving Dr. Zhang and his lead researchers onto Cloud Barkla was quite simple. The Cloud Barkla project, while not live, had all of its information stored within the Alces Flight Center hub. So all the ARC team needed to do was bring forward a change request, and all the information we held was brought back online. First, our team modified the system to meet user requirements using the boilerplate set from our original project. Because strict data protection and security needed to be enabled due to patient samples being used throughout testing, we were required to set up Cloud Barkla on EU West 2, better known as the UK London region. The bulk of the core infrastructure was left mostly intact. We modified user capacity and the amount of storage needed to suit the group. Our biggest change was with the usage of GPUs. The project was set to run in phases in order to maximize the AWS research grant, meaning we needed to keep a close eye on resources. Each phase signaled a change request to our team, who would then modify Cloud Barkla to suit. Let's look at this on a timeline. From the initial point of project launch, the team had access to the basic infrastructure to get their data assets fully cleansed and ready to test. Once happy, the project then transitioned to persistent GPU usage in preparation for their scaled tests. It would come as no surprise that the scaled testing portion of the project was the most compute and cost-intensive, with particular utilization of the quad NVIDIA V100 GPUs for improved performance and turnaround time. As the project scaled down, so did the resources. The first analysis phase took the compute offline to enable Dr. Zhang and his team to target specific models to hone their knowledge on. They then focused on single NVIDIA V100 GPUs for a model run. This targeted resource utilization allowed them to fund one final, focused modeling run, where the quad NVIDIA V100 GPUs were once again utilized to speed time to results. The ARC team then stepped in to ensure that the team data was neatly transitioned back to their on-premises system. As the entire flow is documented, should Dr. Zhang and his team receive further grant funding or need to replicate their work within peer review, the ARC team can bring their work back online through Alces Flight. And that's how we configured and optimized Cloud Barkla.
Hi, I'm Steve Messenger, a HPC Specialist Solutions Architect for Amazon Web Services. I've worked with HPC and cloud technology for longer than I care to remember. I've helped design, configure, and operate many systems, both with AWS and before, everything from small personal clusters to some of the largest supercomputers in Europe. AWS has a number of COVID-19 initiatives. We're part of the COVID-19 HPC Consortium, a large group of organizations working together on research covering many areas. At the time of recording, 43 members and 87 active projects. Members come from several sectors, industry, academia, and many national laboratories and government agencies from across the world. We have a public data lake covering all sorts of COVID data, everything from articles to how many hospital beds are in use. You can find it at the link on the screen. The AWS Diagnostic Development Initiative provides support for innovation in rapid and accurate patient testing and other diagnostic solutions to mitigate future outbreaks. This $20 million fund provides both technical support and AWS credits. HPC is a focus for AWS with a wide variety of services and virtually unlimited capacity. Innovation beyond traditional limits is possible. The capabilities are covered in much more detail in other talks. I recommend you take a look at the other presentations if you want to find out more. AWS has a raft of HPC services, scalable parallel file systems, FSx for Lustre, very fast networking, and a variety of instance types. You can pick the optimum instance for your application. There are many types to choose from: Intel, AMD, and ARM processors, FPGA, GPUs, local NVMe drives, and many other capabilities. Once in the AWS infrastructure, you can also take advantage of many other services, such as machine learning and analytics. You can find more at the link at the bottom of the screen. P3 instances are the instances we used for this project. They're based on Intel CPUs and NVIDIA GPUs. They're a great fit and commonly used for machine learning and HPC applications. They scale from relatively small instances with a single GPU to very large instances. The largest instance type has 8 NVIDIA V100 GPUs, 96 vCPUs, 100 gigabits a second network, 1.8 terabytes of local NVMe, and 768 gigabytes of memory. You can find the P3 instances in 14 different AWS regions, including those in London, as used here. And finally, from me, this slide just has a few of our healthcare partners and customers. Thank you.
Hi, I'm Josh. I'm from the University of Liverpool, and I'm currently working on COVID-19 diagnosis using AI. I'm going to show you the system from the view of the researchers. First, some background on COVID-19. I'm sure everyone will be aware that COVID-19 is a pandemic currently affecting most of the world. COVID-19 is caused by the SARS-CoV-2 virus and causes respiratory illness in most patients. Some patients suffer cardiovascular failure, brain damage, or gastrointestinal disturbance. The long-term effects are still unknown and may only become apparent in the future. The viral sequences are detected by nucleic acid activation tests, such as PCR. Viral RNA is detectable in the upper respiratory tract for up to 3 days before the patient develops symptoms, and is detectable in the lower respiratory tract in the second week of illness. So there appears to be some migration of the virus with time. So if we have PCR testing, then why do we need CT imaging? Well, unfortunately, the presence of virus in the URT peaks around symptom onset and then declines gradually. In some patients, viral RNA may only be detectable for a few days. For others, it could be weeks or even months. In the UK, the NHS actually does not perform PCR testing if symptoms started more than 5 days prior, as testing may return false negatives. Instead, patients are advised to self-isolate for 14 days. But winter is coming, and that means a huge spike in pneumonia cases is expected. The graph on the right displays seasonal trends in NHS hospital admissions for 20 common diagnoses. The red line shows respiratory conditions, of which pneumonia will make a large proportion. If CT needs to be used for more patients admitted 5 days after first experiencing pneumonia symptoms, then we could face a backlog of patients waiting for manual diagnosis. AI is needed to create an automatic diagnosis. With automated diagnosis, a potential pathway would begin with the patient first presenting with pneumonia symptoms. The hospital needs to know whether this is COVID-19 or not. If the patient first experienced symptoms less than 5 days ago, then a PCR test could be used. If symptoms began more than 5 days ago, then imaging must be used to confirm diagnosis. A CT image can be passed on to an AI algorithm, and a diagnosis can be received almost immediately. If the algorithm diagnoses COVID positive, then the patient is treated as COVID positive. But if the algorithm diagnoses COVID negative, then the CT is passed on to a human grader for a manual check. This pathway can be adapted for when PCR testing reaches maximum capacity. This kind of pathway greatly reduces the stress on clinicians. With these considerations in mind, the central aim of the project was to develop an algorithm capable of automatically diagnosing COVID-19 using CT imaging data. We chose to utilize deep learning in our model development. Deep learning is an end-to-end process. This means that we give the algorithm the image and it returns the result. No other intervention from the clinician is needed. The biggest advantage of an end-to-end deep learning model is the ability to automatically extract useful features within the image. Deep learning achieves this using multiple concurrent layers, including convolutional, pooling, and fully connected layers. To develop the model, we obtained CT scans used by Zhang et al. And published in Cell. We experienced many problems in this dataset, mainly arising from the lack of documentation. Cleaning the data was a significant task that should not be underestimated, but was important to provide a good quality, reliable dataset. Security is a huge concern for medical images, but we were able to transfer the images securely to AWS from our own HPC cluster through Alces Flight. Here are some examples of the scans. They are split into 3 classes: healthy, non-COVID pneumonia, and COVID-19. On CT scans, the difference between healthy and non-healthy is quite easy to see, but the difference between non-COVID pneumonia and COVID-19 is much more subtle. COVID-19 is characterized by ground glass opacities and consolidation. A recent study found that radiologists are capable of diagnosing COVID-19 from CT scans with high specificity but lower sensitivity. We used a single scan from each patient. Data was split into 60% for training, 20% for validation, and 20% for holdout testing. The total number of scans for each class is shown here. CT scans are made up of multiple cross-sectional images called slices. Each slice consists of up to 500 of these 2D slices. This results in a scan which is 3D-like, but not exactly 3D, especially when fewer slices are used. These multiple slices result in increased computational complexity over 2D imaging data. To overcome the increased computational cost, high-powered computing is needed. AWS uses NVIDIA V100 GPUs. These increase training speed by 32 times over using a CPU alone. This means that our model trains in days rather than months. We used P3 instances with 4 of these GPUs each to greatly reduce the time taken to get results. Distributing the training across the 4 GPUs greatly sped up our research. To use the AWS instance, we simply log into our Liverpool HPC cluster. Alces Flight then connects us to the AWS instances and controls the job scheduling for us. From our point of view, we are already familiar with our cluster and do not need to worry about learning the AWS system. This means that we are able to begin our research immediately through a familiar interface. So to fulfill the aim, we need a model which analyzes 2D CT slices separately while also considering the relationship between slices. We also aim to classify scans as either normal, pneumonia, or COVID-19. To this end, we developed a model which used convolutional neural networks to extract relevant features. The features are then combined, with the between-slice relationship being modelled. Then the final representation is classified. Here are some brief results. Precision is the proportion of COVID-19 predictions which were correct. Recall is the proportion of COVID-19 cases which were identified. For COVID-19, the model attained a precision of 0.897 and a recall of 0.873. When compared to a previously published state-of-the-art model, we found significantly improved performance. In terms of computing, this system allowed us to utilize larger, more complex models with reduced training time. For our research, we successfully developed a deep learning model to diagnose COVID-19 from CT imaging. The model took into account the between-slice relationship and showed some improved performance over previously published models. We believe that this research will help in the diagnosis of COVID-19 and will also have further applications. For future work, we aim to obtain a second dataset. This dataset will be used to externally validate the proposed model. We also aim to deploy our model on a web application.
Thank you, Josh, and thank you again to all our partners for making this project and this talk possible.